All right. So we're moving back to section 11.3. And we're going to talk about slope as a limit. Now the first thing that I want to talk about is what we're talking about today has to do with some curve. And what we're interested in is at a particular point, we want to figure out right there at that point, what is the slope of our curve? So what we're going to say is we want to look at the tangent line to that curve. So the tangent line just like you talked about when you talked about tangent lines in geometry. Tangent line means the curve and the line intersect in exactly one point there. And the slope of that line is going to be the same as the slope of the curve right at that point. And we use a tangent line. Another reason the tangent line is important is we use that to approximate the curve. So right at that point, you're traveling approximately in a straight line, and the straight line that you're traveling approximately in is that tangent line. So today we're interested in the slope of that tangent line. Now one other thing about tangent lines is if we have a curve like this, and we look at the tangent line, say at this point. Now the line is going to be tangent to the curve at that point, but it can also go through the curve in another point. So those two intersect here and here, but it's only tangent there. We call this the tangent. Even though it intersects the curve at another point, we're only interested in this point. Now, the reason that we're interested in that tangent line, the slope of that tangent line, is the slope tells us about how that function is changing at that point. If the slope is high, that means the function is changing rapidly. It's going uphill. If the slope is low, it's not changing very much. Now what would the slope be if we think of this curve describing the position of some particle, a car, something like that? The slope at that point would give us the velocity of the car or the particle or whatever. So that's another reason that's important. Now what would be the slope of the tangent line right there? What's the slope of that line? 0. What's the slope of this tangent line? 0. It turns out, and it makes sense intuitively, that at a minimum or at a maximum, the slope of the tangent line is 0. So what this gives us, and you'll see this in your calculus class, finding the slope of the tangent line and figuring out where it's 0 will tell us where we have a maximum or a minimum value of our function. And looking for maximum and minimum values is an important thing. So just a little preview of how we're going to apply this. All right. So the way we're going to go about working with the slope as a limit. So I'm going to draw another picture like this on the other page. Are we good with our idea of a tangent line? Okay. So let's look at this. So same kind of curve. Doesn't matter what the curve is. What we want to do is to get at this is we're going to look at the slope of what we call a secant line. So I'm going to make a line between two different points on this curve that cuts through the curve. So we intersect the curve in 2 points. And I'm going to call the coordinates of this point x and f of x. My y value is just the function value. And we're saying this curve is given to us by y equals f of x. So the y value is, we plug our x value into the function, we get the y value. And what I want to do is from this point, I'm going to let my x value change a little bit. And we're going to go up to this new point. And this is going to be a 90-degree angle. And I'm going to let my x value change by h, just some amount, h. Well, this new point is going to be x plus h, because I've gone h additional units in the to the right there. And my y value is going to be f of x plus h. Plug whatever the x value is to my function, and I get my y value. And we're going to find the slope of that line, this green secant line. Well, the rise here is f of x minus h minus f of x, y2 minus y1. That's how much the y value changes. And the run equals h. That's how much we've moved in the x direction. So the slope m is the rise, f of x minus h minus f of x over h. So that gives us the rise over the run for that secant line. Now, what we're interested in is the slope at that one point. This is close, depending on how close that point is. But if our function's changing a lot, if our function suddenly goes uphill or it goes up and down a lot between those two, our slope could be off by a fair amount. So what we want to do is let this point get closer and closer to this point. So in other words, we're letting h get smaller and smaller and smaller. So we're interested in what does the slope get close to as this point gets close to that point. Well, all this stuff that we've been talking about for the last few days is about what functions are getting close to as x gets close to something else. So we're talking about a limit. What we want to do is take the limit, find the limit as this point gets closer and closer to that point. Find the slope as the limit of this quantity as this point gets closer and closer to this point. Well, for this point to get closer and closer to this point, h has to get smaller and smaller and smaller. So at the point, what we're interested in, what we want, we're interested in these things getting close to each other. We want the limit as h approaches 0 of this quantity, f of x minus h minus f of x over h. That's going to give us the slope at that particular point. That tells us as h gets closer to 0, as these 2 points get closer together, what does our slope get close to? So that's how we're going to look at our slope as a limit. This limit is one of the 2 major ideas in calculus. And arguably this is why Newton invented calculus, because he was interested in this problem. How do I figure out how the function is changing right at that one particular point? Now, mathematicians have been working with the concept of a limit for a long time. So, for example, Archimedes, to find the area of a circle, he approximated it with a polygon that was around the circle, and then another one that was inside the circle. So he said, well, the area has to be between the area of the bigger polygon and the smaller one. And then let the polygons have more sides. And as the polygons had more sides, the area of the bigger one and the area of the smaller one were closer and closer to the area of the circle. So that's kind of the concept of a limit, and that's in ancient Greece. They didn't call it a limit, they didn't think of it as a limit, but they had that idea that these things are getting closer and closer together. They call that, or we call it, the method of exhaustion. So eventually you're going to exhaust all the polygons and you're going to get close enough to the area of the circle. So the idea has been around for a long time. So this quantity, this f of x minus h, f of x minus h minus f of x over h, is called the difference quotient. And that difference quotient you will see when you start in your first semester in calculus. This will come up pretty quickly, and you'll work with it much more extensively than we're working with it. All right, so everybody good with the idea of slope as a limit. So what we're interested in today is calculating this limit. So let's look at a couple of examples. We want to find the slope of this graph of y equals x squared plus 1 at a particular point at 1, 2. And when you go further, often you'll just say, find the slope of y equals x squared plus 1. We're interested in the slope of the graph, but we just say, find the slope of y equals x squared plus 1. All right, so here, for this problem, x equals 1. And x plus h is going to be 1 plus h. We have a specific value of 1. So our slope is going to be that limit that we just wrote. Slope is, I'm going to rewrite it here. H approaches 0. F of x plus h minus f of x all over h. And in this case, that's going to be the limit as h approaches 0. F of x plus h. X plus h is 1 plus h. And we're going to plug 1 plus h into our function everywhere we see x. So 1 plus h squared plus 1. This is f of x plus h minus f of x. Well, f of x is 1 squared plus 1. And we're going to divide that by h. Now if we plugged in h equals 0 here, I get 1 squared plus 1 minus 1 squared plus 1, which is 0 over 0. We have 0 over 0, tells us more work to do. So let's do the work. And you'll find as you go on in math, that's always the case. There's more work to do. So we're going to multiply this all out and cancel what we can cancel, all that kind of thing. So we're looking at the limit as h approaches 0. 1 plus h squared is 1 plus 2h plus h squared. So I multiply that out. Plus 1 minus 1 minus 1. I'm going step by step here over h. Well, here I have a 1 and a minus 1 and a 1 and a minus 1. So those all cancel out. So we get the limit as h approaches 0 of, and I'm going to rearrange this, h squared plus 2h over h. Well, now we can factor. What we're trying to do is get to where we can do some cancellation. Well, this is the limit as h approaches 0 of h times h plus 2 over h. So I factored out that common h in the numerator. Well, now we can cancel those. That was kind of what we were going after. And the limit as h approaches 0 of h plus 2 is 2. Because now I can just substitute h equals 0 and not get a problem. So the slope of y equals x squared plus 1 at 1, 2 equals 2. And let's think about this, what this looks like for a second. What is the graph of y equals x squared plus 1? What kind of shape? Parabola. And the plus 1 does what to it? Shifts it up 1. So my graph would look something like this. And at 1, 2, we're at this point approximately right here. And we're saying the slope of that line is 2. All right, questions? Well, what we want to do is we don't want to just be able to, we don't want to calculate the slope at every single different point on a curve. We want to be able to calculate the slope at any point. We want to write this slope as a function that we can plug in some x value to, and we get the slope at that point. So let's take a look at how we're going to go about doing that. It's the same thing, just a slightly different look. Did we have questions? Any questions on that example? Okay. So we want to find the slope. Of the graph of f of x equals 2x squared minus 3 at x f of x. So this is just saying at some point. On the graph. Not at a specific point, but at some point. Well, in this case, x is just going to be x, and x plus h is just x plus h. We're going to plug that into our function. So our slope, I'll write our limit again, just so we see it again. Limit as h approaches 0, f of x plus h minus f of x over h. And in this case, that's going to be the limit as h approaches 0. F of x plus h just means plug in x plus h everywhere we see an x. 2 times x plus h squared minus 3. That is f of x plus h. Minus f of x minus 2x squared minus 3. That's my f of x. And all of that is over h. If we plug in h equals 0 here, we get 2x squared minus 3 minus 2x squared minus 3. So 0 in the numerator and 0 in the denominator. 0 over 0. More work. And we say, well, thank goodness, because it would be really boring. It would probably be really boring if we were done here. We want it to be exciting. All right, so this is going to be the limit as h approaches 0. And we're just going to do all of this stuff. 2 times x plus h squared, x squared plus 2xh plus h squared. Minus 3 minus 2x squared plus 3 when I distribute here. All over h. Hello? Mm-hmm. All right, now let's distribute here. I could have distributed in the same step, but I want to go step by step here so we all see what we're doing. So we get 2x squared plus 4xh plus 2h squared minus 3 minus 2x squared plus 3 all over h. And we think, oh, that looks better. This looks more exciting. Well, we have a 2x squared and a minus 2x squared. We have a minus 3 and a plus 3. So those go away. So we get the limit as h approaches 0. I'm going to rearrange here. 2h squared plus 4xh over h. And what should happen when we do these limits is you should get to where you can cancel out an h. So you don't have that h in the denominator anymore. Well, we have a common factor of h. I'm not going to factor it. I'm just going to cancel it out. So limit as h approaches 0 of 2h plus 4x. I canceled out the common. One of the h's there and the h is there. Now, as h approaches 0, what does this equal? 4x. So this tells us the slope of 2x squared minus 3 is 4x at any point on the graph. So I can plug in x to that function and I get the slope. Yes?
So for questions like those, will we always have like an x in our answer?
Not always. Not always. Usually. Well, when is the slope 0? What x value makes the slope 0? What x value makes 4x equal to 0? 0. Where's the vertex of this parabola? Isn't it at 0, -3? This gives us a new way to find the vertex of a parabola. Find where the slope is 0. Now it turns out in calculus you'll learn a shortcut to figure this out. That will be a lot easier than doing this. But you need to understand this first because this is the foundation. So you'll be able to find the vertex of a parabola without completing the square. Well, you'll still need to know how to complete the square. All right, questions on what we did here? This process, this thing, this function that describes the slope on a graph is so important, it comes up so much, that it gets a special name. We call the limit as h approaches 0, f of x minus h minus f of x, f of x plus h over h is called the derivative of f of x. So that operation, that concept, that function that you get when you find this limit, find the slope of your function at any particular point is called the derivative of the function. And we write f prime of x. That indicates the derivative. We also write dy dx. The dy means the change in y over the change in x. So that's a kind of another way of writing the slope. You'll also see it written as y prime. These are the most, the other way, I'll do one more. df dx, the change in the function as x changes. These are the most common. And these are used kind of interchangeably. Less common, you'll see d dx of f of x. You see that sometimes. And sometimes d sub x of f of x. These are less common. So if the problem asks you to find the derivative of the function, they're saying find this limit. That limit comes up so often it gets a special name. We call that limit the derivative of the function. It's a derivative because it is derived from the function. All right, so I just want to do a couple more examples of calculating derivatives, finding the function that represents the slope of another function. A couple more that are a little more involved than the last two examples that we did. And our homework today and our extra practice tomorrow is just calculating these derivatives, finding these slopes for these various functions. What I told the class yesterday is that the amount of practice that we do with it in here is about 1/10 of the practice you'll do in calculus. It's a very important concept. It's one of the most important concepts in calculus. There's two things you do in calculus, two basic operations: the derivative and the integral. So it's a very important thing. And they're all based on limits. All right. Find the derivative of f of x equals x squared plus x minus 2. So we're finding that limit, f of x plus h minus f of x over h as h approaches 0. So we're looking at the limit as h approaches 0, f of x plus h squared plus x plus h minus 2. That's f of x plus h. Minus, don't forget these parentheses. You run into a lot of difficulties if you forget those parentheses. F of x, x squared plus x minus 2. All over h. And if we plug in h equals 0 here, we get the limit as h approaches 0, we get 0 over 0. Oops, I forgot to write in my little shorthand, f of x. So let's do this algebra. Multiply this stuff out. Limit as h approaches 0, x squared plus 2xh plus h squared plus x plus h minus 2 minus x squared minus x minus plus 2 all over h. When your formula goes halfway across the page, that you're starting to do some serious math. All right, we have a plus x squared and a minus x squared. We have a plus x and a minus x. We have a minus 2 and a plus 2. Those all go away. And what we're left with has a common factor of h. We have an h here, we have an h squared there, we have an h there. So we get the limit as h approaches 0 of h from this one plus 2x from this one plus 1 from that one. So I canceled out the common h's there. And as h approaches 0, this approaches 2x plus 1. So the derivative, f prime of x equals 2x plus 1. And if we plug in any value of x, that will be the slope of the tangent line at that particular point. When is the derivative equal to 0 here? When x equals negative 1/2. If we completed the square here, we divide 1 by 2 and square it. Our vertex would be at 1/2. X equals 1/2. Our y value would be, what, 1/4? Something like that? 2 plus 1/4. So that gives us, we can find our vertex. We know the derivative, we can find the vertex of the parabola really easily. And we know the vertex is where we got a minimum or a maximum. So we have all kinds of information from the derivative. Questions? Okay, let's look at one more interesting function. Not quite as long as this one. Find the derivative of f of x equals 1 over x. So we want the limit. Instead of m, I'm going to say f prime of x equals the limit as h approaches 0, f of x plus h, 1 over x plus h, minus f of x, minus 1 over x, all over h. H approaches 0. All right. Didn't we do some homework problems like these just the other day? What do we have to do here? We need to subtract these two fractions. So we need a common denominator in the numerator. So I'm going to multiply this by x plus h over x plus h. And I'm going to multiply this by x over x. So we get the limit as h approaches 0. In the numerator, I get x minus x plus h over my common denominator, x times x plus h, all over h. And this equals the limit as h approaches 0. X, we get an x minus x and a minus h. We get a minus h over x times x plus h over h. Well, the h in the numerator cancels with the h in the denominator. And if you don't see that, you could think of this as h over 1. And we're multiplying by the reciprocal, so those h's cancel. And I get that this is the limit as h approaches 0 of minus 1 over x times x plus h. And now we can plug in h equals 0. And as h approaches 0, this approaches negative 1 over x squared as h approaches 0. So the derivative f prime of 1 over x equals negative 1 over x squared. When is this equal to 0? Never. 1 over x, f of x equals 1 over x doesn't have a maximum or minimum. And if we graph it, 1 over x, remember, looks like this. Doesn't have a maximum or minimum. But it's bottom heavy, so it has a horizontal asymptote at y equals 0. The limit as x approaches infinity is 0. And as x approaches infinity here, the slope approaches 0, which makes sense. Almost horizontal. Not quite, but almost. All right. Questions? How does calculus taste? Pretty sweet to me. It's like candy. Okay, a couple of reminders for the homework. This will show up in the homework. So you'll be asked to find the equation of the tangent line. So point slope form. Thank you. When we find the equation of a tangent line, we'll have a point on our graph. There's our point. We'll be able to find the slope from the derivative. Y minus y1 equals m x minus x1. M is the slope. x1, y1 is the point. When you get to calculus, point slope form is really the only form of lines you really need. You don't need any other kind. So anybody in the past that might have told you point slope form is not important was incorrect.
I love how all the teachers know that Lucky doesn't teach it.
I just said if anyone ever told you that. I'm not saying anybody specific. Horizontal lines. What is the slope of any horizontal line? Horizontal line. Slope equals 0. Vertical line. Slope is undefined. So you might be asked to find when the tangent line is horizontal and when the tangent line is vertical. So it's asking you about the slope. Okay. In my geometry class, regular geometry class, we just had a homework assignment on page 777. So it's kind of a strange coincidence. All right, there we go.